Hello everybody and welcome back to the channel. I hope you're all having a great week. I personally am not because my net worth has gone down around 20% thanks to Mr. Donnie J. Trump. Now, what upsets me the most about this whole thing is not really even necessarily how much money I've lost or the fact that, he's made hundreds of millions of dollars through his pump and dump. But what really makes me the most upset is that whenever I do a pump and dump, I just get an angry voicemail out of it and no extra money. So I'm going to keep stewing, but in the meantime, let's go talk about Apache Cassandra. All right, so let's go ahead and get started. Cassandra is a paper out of Facebook from 2009. You can see I crossed out my wrong date over here, so we're already off to a hot start. Now basically, Cassandra is something that they made there for the inbox search problem, which is basically running an inverted index amongst the messages that you get in Facebook Messenger. So that's hopefully simple enough and easy enough to understand, but basically they take a ton of influence from the Amazon Dynamo system. And so the paper itself is not super in-depth, partially because there's a ton of small details, but there's also a lot of literature that already covers a lot of this system. And so probably the main focus of my paper is just, or of this video rather, is going to be kind of where the system differentiates itself from Dynamo on a few different key points. But basically, the motivations for creating it in the first place, obviously Dynamo was proprietary, so it's not like they could just go ahead and use it, but they could build something similar, and so that's what they did. So they wanted really, really high availability and also super high write throughput. So the high availability thing is important because, when you use your typical single leader system, even if you're able to tolerate a leader failure and perform some sort of failover, that typically takes a few seconds to perform. You have to figure out that the leader's down. You potentially have to wait for some sort of leader lease to expire, and then you have to now perform a new leader election. And additionally, Dynamo, even though it is focused on high availability and to some extent write throughput, like at the end of the day, you're still making a bunch of quorum writes, and you're not necessarily using the most write optimized structure within the database itself, so Cassandra tries to improve upon that. Cool, so let's go over the differences at a really, really high level, and then we'll dive in a little bit more. So basically, instead of using vector clocks or version vectors, we're now doing timestamp resolution. We'll talk about why this is a little bit better in terms of achieving high write throughput. We're using LSM trees and SS tables. Hopefully you guys are, pretty well adapted with those at this point if you've been watching this channel for a while. We're doing adaptive partition rebalancing. This isn't necessarily going to make it better for write throughput. I mean, it should in theory, but it's just a difference from Dynamo. We're doing better kind of replication policies to be a little bit smarter about our topologies that we're using. A little bit of centralized coordination, which is kind of against the whole philosophy of Dynamo, where they don't want a single centralized anything, because they want everything to be completely homogeneous in terms of all systems or, kind of all nodes within the system, so you don't have any single points of failure, but that's not really going to be the case here. And then finally, probabilistic failure detection, which we'll talk about in a little bit as well. Before we do that, let's just dive into what Cassandra is at a really high level. As we know, or if you've watched any of the videos on my channel about it, it is very much a leaderless database, meaning we're mostly relying on read quorums and write quorums to get consistency of our data. But even stepping back from that point, it is basically a NoSQL database where we've got a bunch of keys and then associated column families. And think of each column family basically like its own table, insofar as that's the data that's stored together on disk. And then, you can have a sort order within that table. So you can have, this concept of partition keys, and also even within that, you can have sort keys that allow you to have multiple values for a partition key. And so basically, they don't really, at least in the initial version of Cassandra, I'm not entirely sure how this has changed because I'm mostly going off the paper for this video. At least in the initial version, things are only going to be atomic at the row level. So you can't make writes to multiple keys at one time and make them atomic. It's something in the paper that they say they actively want to work on because a lot of people want that type of feature, but for now it is just going to be atomic at row level. And notice that it's not even going to be for all replicas at once. So for example, if you're doing a write to multiple replicas at a time, you can actually have those writes interleaved at each replica with the writes from someone else. So if I've got two replicas right here and I've got two people, basically this guy can write first here, this guy can write first here, and then his second write comes in and the second write goes over here first, and this guy's second write comes in second. And since we're using timestamp resolution, now those writes were applied in different orders at both replicas. So this is kind of what stops Cassandra from being, perfectly or strongly consistent or linearizable. Cool. So the first thing that I mentioned on my list of high-level differences between Cassandra and Dynamo is basically that we're ditching vector clocks now. Now in Dynamo, in the paper, if I recall correctly, it's been a while, I do believe that they allow using timestamp resolution as well, but in Cassandra you have to do timestamp resolution. So if you recall, vector clocks are really nice when you're doing something like a multi-leader database because it allows you to detect when two writes are concurrent. So for example, if I'm client 1 over here, and then we've got client 2 on the right, basically what your vector clock is saying is, it's reflecting what databases you've read from in the past and what information you've actually seen. So if this guy's vector is saying 2, 0, 0, maybe it's saying that 2 updates were applied to this database and our client 1 has seen both of them. If this guy is seeing 0, 0, 1, maybe it means that 1 update has been applied to key X. So 2 updates to key X on this left database, 1 update to key X on this right database. They haven't yet converged. There hasn't been any anti-entropy or anything like that. Client 2 has only seen that one from the right database, and then now they go ahead and write to this third database. Now the third database can tell that these two are going to be concurrent writes because they couldn't have known about one another, because when you look at these two version vectors, they're overlapping, right? So 2 is greater than 0 in the first index, but then 1 is greater than 0 in the last index, and so they must be concurrent. So then this database is able to store them as siblings and treat them a little bit differently and do either client-side resolution because it'll hand both values to the client and say merge these together, or it can possibly resolve those on its own. That being said, what Cassandra does is it just uses a timestamp. The reason for doing that is because if you're using vector clocks, each client needs to first read from the database in order to get a current state of the data before writing back to it, because you need to establish this kind of causality relationship and determine whether writes are concurrent or not. That being said, when you're using timestamp resolution, you never have to actually read from the database to get some data before writing back to it. You can basically just go ahead and write, and you'll use some arbitrary timestamp. Now, it's absolutely going to be the case that there are downsides to timestamp resolution, the main one being that if someone writes and then I write literally a nanosecond later, I clobber their write, and it's as if it never even happened. That being said, Cassandra is not a system that's really opting for incredible data consistency. It's opting for high availability and high write throughput, and so they're okay with using this timestamp resolution. Just really high level, going over what reads and writes in Cassandra look like. When we're reading, you basically have two options. You can either read from a quorum of nodes, which means a majority of them, right? So we'll only respond once we've heard from a majority of nodes. Or you can do so basically at the closest replica. So over here, if I've got, these three databases, right? So this one has version 30 initially. This one has version 30, or timestamp 30 for key X, and this one has timestamp 31. If we read from a quorum of nodes, and maybe all three of them happen to respond this time, that's great. We only needed to hear from two of them, but all three respond. What we're now going to do is also perform something known as read repair, where we take the data with the most recent version, and then we push it back to all of the stale replicas. So now version 30 can be bumped to version 31 because it is hearing about newer data that it didn't necessarily happen to have. Cool. And again, that's configurable, right? So if this is the closest replica to me, depending on my settings for how I set up Cassandra, I can either just read from that one, or I can read from a quorum of nodes. So if I read from a quorum, I should expect that every single write that I make is going to be reflected in my read. If I read from the closest replica, I should expect that the latency is going to be lowest, but I may have some stale reads. Cool. And then writes can be performed either synchronously or asynchronously. So if they're performed synchronously, it means that my write, or Cassandra is not going to report to me that my write was complete until it has heard back from a quorum of nodes saying we processed your write successfully. Asynchronously would basically mean, either I just write to the first node over here and it responds to me saying you're good, and then it goes to a quorum in the background, or potentially it could even just mean you call some random endpoint. You never even hear from the first server. I assume it's the former of those two, but it doesn't explicitly say in the paper. Okay, let's talk about partitioning and replication. Systems like Cassandra and Dynamo, those both very heavily rely on consistent hashing. So for those of you who just need a quick refresher, consistent hashing is basically saying you organize all of the key ranges on a ring. And so if this is node 1, Node 1 is responsible for all of the keys that fall in this range until we find the beginning of Node 2's key range. Great. So the idea here is that in Dynamo, you'll basically have nodes taking multiple positions on a ring, and occasionally you may actually even have like these pre-sliced up partitions, and you can hand small partitions from one node to another in order to alleviate them. In Cassandra, you can actually basically just like freely move around the ring, and they do so very little at a time to basically tune nodes such that ones that are heavily loaded can actually alleviate, or can be alleviated by ones that have free space, or ones that are currently less loaded. So this is really nice. When they do that, the node that was heavily loaded now has to send all of its data over to the one with less load. And so they'll use like kernel to kernel zero copy techniques to do so over the network, just to make that as fast as possible. You don't have to load any data into the user space before sending it. And then they mention in the paper that one thing they want to do in the future is they hope to parallelize this process across different replicas. So obviously, like any other fault-tolerant database, Cassandra does have replicas for all of the data. And so if one particular node is now going to act as a replica for some key range, and you have 3 other replicas that currently hold that data, they can all send one subset of the data in parallel to the receiving node to speed things up. And so again, like I mentioned, in Dynamo, this is a little bit different. You can't just freely move around the circle. Rather than having nodes that are freely moving around, they'll have multiple different locations for nodes, and they'll kind of give them a certain amount of tokens on a hash range. And another difference between Cassandra and Dynamo, at least as far as I can recall from the Dynamo paper, is this concept of having multiple replication policies. So the one that Dynamo uses is called rack unaware, which is still possible in Cassandra, but basically it means you don't consider where the actual servers themselves are located. You just look on the hash ring itself, and you choose the next few nodes. So maybe this guy and this guy are replicas for this key range as well, if this is node 3 and we need 3 replicas. However, that's not always going to be the best thing, because if node 1, node 2, and node 3 are all located in the same rack, that means they have the same failure domain, aka that rack goes down and then that data becomes unavailable. So rack aware basically means you want to spread the replicas for a given key range out within the same data center, but different racks, so you're less prone to rack failures taking out your data. And then data center aware takes that even a step beyond that and basically says, okay, we're going to put these nodes, or the replicas for this key range, in different data centers that are ideally still pretty close to one another, such that they're connected by high-speed network links. And so what this is going to accomplish is it's just going to greatly decrease the percent chance of having a correlated failure, which is going to be very, very good. That being said, making decisions like these, where you're basically evenly spreading out the key range across nodes based on their rack properties and their data center properties, is not a trivial one to make. So the way that Cassandra actually decides to do this is, rather than keeping everything decentralized and coming to some sort of decentralized consensus about where every single replica should live, instead what it does is it employs Zookeeper. So what Zookeeper is used for is Zookeeper basically just sits there. Zookeeper is going to elect one particular Cassandra node as the leader, and then the leader is going to basically figure out these replication topology decisions and try and balance out the key ranges that belong on each node, so that all of them are basically supporting the configured number of replicas. So otherwise this would be very tough, but by electing a single leader, they greatly simplify the process. Now this is something that we see in a lot of the other papers that we read. Like, a lot of the designs that we've seen up to this point do involve some sort of single leader or master node that makes a lot of scheduling decisions or things along those lines, and this is no different. So this kind of departs from the Dynamo philosophy a little bit, but ultimately in the conclusion of this paper they say it's better to use a single leader when it makes reasoning about the system much more simple, even if it does make us susceptible to things like failovers. Okay, membership. This is kind of one of those things that's also, I actually can't recall if they do this in Dynamo, but it's very much something that we've covered on this channel, which is that Cassandra uses a gossip protocol, which is basically just nodes, screaming at other nodes in any random order, and then by virtue of doing that, information gets dissipated through the cluster eventually, and everyone hears about updates to the cluster. So they use UDP for doing so, which is good because you're going to have, basically just less overhead in your packets, and you're not going to have any flow control, so ideally it should go faster. Also non-blocking I/O, so threads aren't going to block and wait for packets to come back as a response. They just send their packet, and then a packet comes back, and then you'll spin up a new thread and a thread pool to handle it. As far as determining whether nodes in the cluster are up or down, this is always going to be very important because you need to know which replica to reach out to. So in Cassandra, as opposed to kind of doing some sort of localized binary, this node is up, this node is down type of failure detection, what they do instead is they use this thing called a phi accrual failure detector. And so what that really means is it's probabilistic. So if I'm a node and I'm thinking about reaching out to another node in the cluster, I need to know if it's up or down. But I won't actually determine that. Instead, I'll kind of basically make a probabilistic estimation that it's up or down based on the gossip that I'm receiving from the other nodes in the cluster. And so the phi value that they use in Cassandra is tunable, where basically the higher phi that you use, the less likely you are of making a false negative, where a false negative would just be like, I think this node is down, so I'm not going to reach out to it, but oh wait, it turns out it's actually not down. I got a heartbeat a couple of seconds later. So in practice, they find that it takes them about 15 seconds to detect when a node is down using phi accrual, and this is in contrast to other traditional failure detection systems that they tried, which were taking them like 2 minutes in the same size cluster. So this is obviously going to be a pretty big game changer for them in terms of figuring out when nodes are up and down. Now, another thing to note is that we do sloppy quorums in Cassandra. I didn't explicitly mention that, but I wrote it on a previous slide, where a sloppy quorum is basically saying, like, if there aren't enough replicas up right now that are currently holding this key range, then basically pick another one of the nodes in the cluster and temporarily use that to make a quorum. So this is going to also, kind of contribute towards breaking strong consistency in favor of having better availability within the cluster. Now, it's worth noting that when you add a new node to the cluster, it needs to perform gossip, right? But the question is, how can it perform gossip if it doesn't know who to gossip with, and how's it going to receive gossip if none of the nodes in the cluster know about it? Well, we've got a couple of like bootstrap or seed nodes that you can either hard code configure into any new node that you're adding to a Cassandra cluster, or additionally, you can also put those locations in Zookeeper and then hard code the Zookeeper configuration into each Cassandra node so that it has a couple of nodes to start gossiping with, and then that way it'll start receiving gossip as well. Once those two seed nodes are aware that it exists, they'll start gossiping to it as well. Okay, so what do writes look like internally in Cassandra? Well, this is going to use our pretty standard LSM tree plus SS table architecture. Now, I've made plenty of videos about this one, so I'm not going to go too crazy with it here, but high level, the idea is the first thing that you do every single time you make a write in Cassandra is you write to a commit log. So you can do this either synchronously or asynchronously. Asynchronously means that first these writes into the commit log would be buffered in memory, and then they would be flushed in batch. But note that every single write into this commit log is always going to be sequential, which is good because the commit log is on disk. Whenever you're making writes to disk, you want them to be as sequential as possible because random writes on hard drives are always going to be slower. The second thing that we do after putting the entry in the commit log and making it durable is we flush it into our LSM tree. So I'm not entirely sure that they actually do use an LSM tree in Cassandra. They call it a mem table. I'm pretty sure in the past when I've researched this, it is an LSM tree. But the point is you have this in-memory data structure that's going to be keeping the keys sorted in the order that we want them internally. And then eventually, at some point, this mem tree or this mem table is going to get too big, and we're going to flush it to disk. So when we flush it to this particular file right here, which is called an SS table. Now, the SS table has a few properties to it. For starters, it's sorted in the proper order. Note that because it's sorted, that means that all writes that are going to it are also going to be sequential, because when we flush this guy, it's also sorted. So we're basically just writing to disk in the order that the mem table tells us to, which is going to be very efficient. Again, the fewer random writes to disk, the better. It's also got a Bloom filter associated with it, which we'll cover in a second. The reason why it has a Bloom filter is because when we're looking for the values of keys in Cassandra, the first thing that we're going to do is check the mem table to see if it's in there, because the mem table would have the newest value of it if it existed. Then we'll check the newest SS table, and then after that, if it's not there, we're going to check older SS tables in order from newest to oldest. That being said, this is going to be kind of expensive, right? We're reading from a lot of files on disk. So what would optimize it is using a Bloom filter, and a Bloom filter is going to tell us very quickly if a key that we're interested in is not within a particular SS table, so then we can skip reading it, and it's going to speed up our reads considerably. Note also that because these SS tables are sorted, we can benefit a lot by having a sparse index, and they do so in Cassandra. So every, I believe, 128 keys or so, you'll have something that you keep in memory, like a block index, that's going to allow you to quickly binary search a file and find the offset of a particular key. Also, for tables with a lot of columns, they also do a separate column index, so you can quickly jump into the right offset within a file to figure out where a certain row column offset lies, so you don't have to read as much data. And then finally, we also have to do compaction, right? Because at the end of the day, when you're doing an SS table, you're going to have a lot of these files, and they're actually going to have duplicate keys in them because all of these files are completely immutable. So eventually, you're going to be storing a bunch of redundant data because, maybe you'll have key X and it's got some old value in here, and then you'll have key X and it's got its new value in here. And this is now completely irrelevant. So when we compact them, we're basically doing, a merge of those two files. We're merging two sorted lists. And then we can go ahead and get rid of this piece and now just have one combined SS table file to read from, which is also going to speed up reads. In Cassandra compactions, they only try and compact files of similar size, and then they also have major compactions that compact every SS table file at once. Now, a really nice thing about the LSM tree plus the SS tables compared to something like a B tree is that you don't actually need to grab any locks when you're performing reads or performing writes. The reason is that all of these files are completely immutable, right? So it's like you're reading from a consistent snapshot every single time that you do so. And as a result of that, the amount of locks that you have to grab for something like, two-phase locking with a B tree is significantly lower in LSM trees and SS tables because you're just reading these immutable files. So the database community has very much been kind of moving in this direction for a while now, especially in analytical databases, because you just read consistent snapshots, you get snapshot consistency, you don't have to grab any locks, which is really great. Okay, the last thing to do before we conclude this video is talk about commit log rolling. So basically the idea behind this is that we're going to have all of these commit logs from step 1, and you don't really need commit logs once your SS table, once your LSM tree that corresponds to the writes in that commit log is flushed to disk, right? It's just not important anymore. It's persisted, so you can clean that data up and save some data on disk. So basically each commit log in its header is going to have a bit vector, and that bit vector is also going to be stored in memory for easy access or for caching it. And basically that header is just going to be a bunch of 1s and 0s that indicate whether all of the LSM trees that are being referred to, like this write that's in this entry of a commit log is also located in some sort of LSM tree. And so once this LSM tree gets flushed to an SS table, we can basically put a little bit over in here indicating that that's the case. And so once all of the LSM trees that are represented within a given commit log have been flushed, we can actually just go ahead and get rid of this thing and clean up its space. Now, even if something like this guy seems like it's ready to be flushed right here, if this is an older commit log, we also need to make sure that this guy is ready to be flushed, or else we can't yet flush this guy. So hopefully that all makes sense. Let's go ahead and move on to the conclusion. Like we mentioned, Cassandra is going for high availability and large write throughput. Obviously, if it were going for consistency, we might see a greatly different system design, but it's not. This is what we were looking for, and this is ultimately what they got out of it. There are also a few changes compared to Dynamo, which do make a lot of sense in their context. For starters, they can detect failures really fast by doing so probabilistically and via their gossip protocol. They get very nice load balancing compared to Dynamo because they're willing to basically consistently tweak what ranges of keys each node is holding so that they can get a kind of optimal balance. Number 3 is that unlike Dynamo, which if I recall uses like a pretty standard B tree for their database engine, these guys are using LSM trees and SS tables, which means that they're really getting write optimized writes within their systems. And then finally, in certain cases, when you're doing complex operations and trying to balance partitions and balance which nodes hold which replicas, using leader nodes to do so is going to make that decision a whole lot more simple rather than relying on some sort of distributed consensus mechanism. Involving Zookeeper, even though it is in some senses a point of failure, makes their system design much easier, and so they feel that it is very much worth it. Anyways, guys, hope you enjoyed this video. A bit of a busy week for me next week, so I may do a shorter one or a non-technical one, but I look forward to seeing you, and have a great weekend.